Good morning, good afternoon, good evening, everyone. I would like to thank the organizers of this event for giving me the opportunity to talk about my research. Today I'm going to present the material science underpinning the long-term performance of alkali-activated concretes. I'm Susan Bernal from the School of Civil Engineering at the University of Leeds. Alkali-activated materials are alternative cements that are produced by a chemical reaction between an aluminum silicate source or a precursor and an alkali source or activator, whose function is promote the dissolution of this precursor and then the precipitation polycondensation of reaction products. The final cement that we produce will look like a synthetic rock. In the past, the application of alkali-activated materials have been quite limited to some very specific projects, but over the past 3 to 5 years, there have been a growing interest in this technology, mainly because of the opportunity to become one of the solutions to achieve net zero targets by the infrastructure sector. Some of these examples, for example, are the creation of new standards enable the use of these materials in structural and non-structural applications, but also some major Poland cement producers like LafargeHolcim are doing tremendous development in this technology. And also we can see, for example, in the UK, how our main roads authority, Highways England, is trialing these materials in some of the major roads in the country. One of the main incentives for adoption of alkali-activated materials is their sustainable credentials, particularly their potential to offer significant CO2 savings compared to commercially available cements or other alternative cements that are currently in the market. In this graphic, we can see the relative CO2 allocated to blended Poland cements and alternative cements. And if we look into the uncertain range of relative CO2 reductions, we can see that we can achieve between 40 to 80% savings in CO2 emissions, which is significantly a higher reduction compared with any other type of cement. It is very worthwhile to continue developing this technology and adopting this technology, as I say, as one of the many alternatives that we need to implement in the years to come to achieve net zero targets by the infrastructure sector. But because you don't have just to take my word, actually LafargeHolcim, for the specific alkali-activated cement formulations they are producing, they claim that they can achieve up to 70% of CO2 reductions in comparison with some conventional Poland cement concretes. I think this is quite remarkable and a very good incentive to continue developing this research. But one of the things about alkali-activated materials, and I will say with many other materials in general, is that people have this tendency to generalize properties and performance, which should not be the case. When we talk about alkali-activated cements, there are many factors that will control the phase assemblage and therefore the performance of the material when it's put in service. In the case of alkali-activated slag cements, we have identified that when we use different types of activator as a function of the slag chemistry, we can favor the formation of different secondary reaction products. And I will say these particular type of products are often overlooked, but these ones play a key role, particularly in the durability of these materials. What I want to say is that we need to move from this general overview about how alkali-activated cements are going to perform and instead try to select the most effective activator to promote a certain microstructure that will provide some specific properties to the cements that we want to produce. So today I'm just going to mention a couple of cases of study related to durability. The first one is carbonation of alkali-activated materials. Historically, carbonation has been perceived as one of the major barriers to adoption of alkali-activated cements because it's believed that they are far more susceptible to carbonation degradation compared with Portland cement. However, in a recent review done by the RILEM-TC 281 CCC Working Group 6, we actually compare alkali-activated cement with those Portland blended cement with high contents of SCMs. And what is more striking from this review that we have done is that actually alkali-activated slag concretes present very similar performance, at least in terms of carbonation, than many of the blended Portland cement systems that we currently use. So this suggests that we have to also have this mind shift towards how these new materials are going to perform. So we try to investigate and determine why there was such variability in the outcomes regarding carbonation performance of alkali-activated cements. So in a very early study, we evaluated the effect of the slag chemical composition and the carbonation depths that these materials will develop under natural conditions. And we identified that the slag chemistry had a tremendous effect on the carbonation rate that we could identify. So, for example, we can see that as the magnesium oxide content in the slag increased, the carbonation depth can be reduced up to 90% compared with alkali-activated slag cement produced with a slag with much higher aluminum content and reduced magnesium oxide content. So this was a very interesting finding because it's evidence that there is plenty of opportunity for us to control how alkali-activated slag cements can perform, at least in front of carbonation. So in the case of sodium silicate activated slags, we have identified that using slags with different chemical composition leads to the formation, particularly of different secondary reaction products. In this case, layer double hydroxides like AFM or hydrotalcite, which play a key role, for example, in the chemical binding of different species such as CO2 or chlorides. So we identified, for example, in some specimens that were designed to achieve the same compressive strength but produced with different slags, that when we have a slag with a higher magnesium content, the carbonation depth is reduced like by 50%. So the findings of the interlink between the slag chemistry and the reaction products that are formed in these systems when we use sodium silicate inspire us to start looking at different alkali-activated slag systems. So in this case, I'm showing you some of the results of sodium carbonate activated slags. We use 4 different slags in this case with different magnesium contents, where we can see that the changes in slag chemistry have a strong influence in the kinetics of reaction of the material. So for example, I will say in the past, sodium carbonate was not considered an effective activator to produce alkali-activated slag cements because the majority of studies reported a very long setting time. But we identified that can be controlled if we select slags with higher magnesium content. But also, the secondary reaction products formed in these systems are completely different. So depending on what we want to achieve from our material, we can also select the right slag with the right activator and promote certain performance that we want to see. So for example, from the durability perspective, when we think about chloride or CO2, is very interesting and important to promote formation of these layered double hydroxides type phases. So when we expose sodium carbonate activated slag mortars to CO2, the results were quite interesting because usually these materials develop lower compressive strength than silicate activated slag cements. So we might expect a reduced durability performance, but it was completely the opposite. What's really interesting to look here is the fact that we can see how under natural carbonation conditions, the compressive strength of the material continues to evolve over time, which is something that we might expect. But when we do carbonation under accelerated conditions, although we don't see an increase of the compressive strength in this material over time, we do not see a decrease, which is completely different to what is typically observed in these materials, which indicates that sodium carbonate activated slags can withstand, for example, carbonation far better than sodium silicate ones. And we can see in this curve down here that carbonation is actually happening. And this also indicates that the mechanisms of carbonation when we use different types of activator are completely different. So again, we can't generalize how alkali-activated materials will perform. The old experimental data that we collected for this particular degradation mechanism over years actually inspired to start developing prediction tools that would enable us to have a rough idea how our alkali-activated slag cements will perform in terms of carbonation as a function of the slag chemistry, the activator used, and of course the degree of reaction that we can achieve in those systems. So in a recent publication by Xinwen Qi, I give all the credit of this amazing work to her. We developed some thermodynamic modeling predictions of carbonation of sodium silicate activated slags and sodium carbonate activated slags. So what is really interesting to see here is when or what's happening in our material when we start identifying pH changes, because as we all know, when we evaluate carbonation, we rely, for example, in pH indicators such as phenolphthalein. So it's really important to know if there is any sort of correlation between those pH changes and potential degradation of the material. So what is really interesting to see in this case is the fact that the major drops in pH in both cases are going to happen when all the cache phase or the main binding phase is fully carbonated. But a lot of things will need to happen within the material before the consumption of the cache phase actually takes place. And all these models and predictions actually indicate that the presence of reaction products such as hydroalkydes, hemicarbonates, or secondary reaction products seem to buffer the pore solution pH and how carbonation proceeds which is something that we have also observed from the experimental data. So when we think about carbonation, what is very interesting for us is thinking about corrosion, how the corrosion of a steel rebar will proceed in a material that is fully carbonated. So thinking about that, some simulations were performed when the specimens were expected to have a pH of 12.5. So this particular value of pH was taken into consideration because it's the change boundary of the phenolphthalein indicator that we typically use to determine a carbonation depth in cement and concretes, but also because the stability of the oxide film that is formed in the steel rebars will be less stable at pH lower than 12.5. So in this case, what we did was try to determine the phase assemblage of alkali-activated cement for a given aluminum oxide content within the slag, changing the amount of magnesium oxide in the system. So we can see that there are tremendous changes in the phase assemblage of sodium silicate and sodium carbonate activated systems depending on the chemical composition of the starting raw materials, and that of course carbonation in many instances will also have an impact in what type of reaction products will be formed. So I would like to drive your attention particularly to the samples with a slightly lower aluminum content, because what we can see here is that for a very high magnesium content in the slag and a low aluminum content, we have higher, or we can expect a higher content of cash phases and secondary reaction products for the same degree of reaction that we will do, for example, if we have a reduced content of magnesium oxide and a high content of aluminum oxide in the cements. We can see a similar trend here, for example, when we use sodium carbonate activated slag. And as I said before, it seems like the fact that we have all these secondary reaction products is really positive for CO2 uptake in alkali-activated slag cements. So the second case of study is, of course, chloride permeability of alkali-activated materials. People working in this area perhaps know that alkali-activated cements are always considered like to present very, very high performance when we evaluate them against chlorides. So I'm not going to go into much detail about what other people has reported in the area, but what I want to mention today is, for example, for the case of sodium carbonate activated slag mortars, we wanted to trial if we had higher contents of layer double hydroxides in our cements, if that will have a positive impact in the chloride permeability in these materials. So we produced two different mortars that were added with calcined layer double hydroxides, different contents, relatively small contents, and we can see that even adding this very tiny amount of layer double hydroxide, the chloride migration coefficients for these cements significantly reduce. So this will have a significant impact in the long-term performance of these materials. So the reason for these differences in performance when we have different contents of layer double hydroxides in our sodium carbonate activated slag cements actually lies on the type of reaction products that we identified in the samples after we immerse them in a chloride-rich solution for a long period of time. So we can see that actually in these systems we favor information of layer double hydroxide type phases that can easily chemically bind chlorides or carbonates. And also we can see in these isotherms the amount of chlorides that can be absorbed in different specimens that we tested. So following a similar approach that the one I presented for carbonation of alkali-activated materials, we have used also thermodynamic modeling to predict the phase assemblages or the type and amount of reaction products that we can expect in alkali activators like cement as a function of the type of activator we use and as a function of the slag chemistry that we are using as well. So here I'm presenting just these phase assemblages for 7 different slags activated with sodium silicate and sodium carbonate. We can significantly see the changes in the reaction products here. And actually, because we know which phases will chemically bind chlorides, and we also have information about the chloride diffusion coefficients for a lot of the materials that we have modeled and here, we could actually infer the correlation between the chloride binding capacity of different alkali-activated cement systems as a function of the activator that we have used and the slag composition. So this is an overview here when we show how different types of phase assemblages will promote more chemically binding. So in this particular model that was developed to infer transport of chlorides, we can predict actually the content of chlorides in the concrete cover layer, or at least in the cement part of the concrete cover layer, as a function of time and also as a function of the chemical composition of the precursors and the activators that we can use to produce this cement. So to conclude, I think that there are some very clear messages I would like to share with you today. The first one is that we need to shift this mentality of generalizing concepts regarding durability of alkali-activated materials because it is clear and we have the evidence that there are many factors that will play a key role on how these materials will perform, for example, when exposed to CO2 and also when exposed to chlorides. So it is clear, of course, that there is a strong correlation between factors controlling the phase assemblage evolution and durability. And I will say we need to pay particular attention to the secondary reaction products forming these cements because they seem to be the ones playing a key role. But also, I would like to say that we need to do far more research to understand the chemistry and nanostructure of the cache phases forming in alkali-activated cement systems, which are different to those that we can expect in blended cement systems, because we really don't know yet what is causing these materials or these phases to be more prone to carbonation, and we also need to find out, for example, what is their chloride binding capacity. So I think this is something that really needs to be explored, and it will be very beneficial not just for the area of alkali-activated materials, but also for the area of blended pollen systems. So another very important message today is that slight variations in mix design lead to notable changes in performance of alkali-activated materials. So we need to identify what are the trade-offs that we can make when we produce these materials when we think about durability. So in the past, I will say one of the main motivations for selection of the activator has been producing concrete with the highest strength possible. But we have seen from our research that perhaps other activators like sodium carbonate that might have a better environmental credentials than sodium silicate, yes, we will not be able to develop concrete with such high compressive strength, but we can develop concretes with improved durability, particularly when exposed to carbonation. So we need to evaluate and determine what do we want to achieve and what will be more sustainable in the longer term, producing a lower strength but higher durability concrete or a super strong concrete that might have some issues of durability in the longer run. So finally, and I think this is one of the things I really like the most about alkali-activated materials, is that they are so versatile, because when we have different precursors with different chemical compositions, when we have different activators and we dose them in different ways, we can really tailor-made or produce bespoke concretes for specific applications. And I think we already have a good understanding of when or how we can produce these concretes, particularly when we think about carbonation of chloride permeability resistance. So again, the message is we can produce alkali-activated concretes that can withstand the test of time. But I will say another very important thing that we need to bear in mind is how are we testing this long-term durability performance of alkali-activated concretes. So I didn't have opportunity to discuss about that in this presentation due to time restrictions, but we need to be a little bit more critical about the type of testing methodologies that we're following to determine performance of alternative cements. We need to bear in mind that a lot of the standards and tests that we apply have not been designed thinking about alkali-activated materials, have been designed for testing completely different materials that will perform differently in the exposure environments. So we need to be very critical about the applicability of this test, because we can get misleading results, and those misleading results end up in these generalized concepts that prevent the widespread use of very valuable materials that I believe will play a key role in the years to come. So I would like to thank you for your attention. I hope this talk was of your interest, and I will be more than happy to answer any questions.